Hello friends, my name is Anurag Tulsiram. I am a grad student in the Electrical and Computer Engineering department at the University of Florida. I am going to give a presentation about my project Detection of Acute Lymphoblastic Leukemia ALL in Blood Microscopic Images. This project was submitted in partial fulfillment of requirements for the course EEE 6512 Image Processing and Computer Vision and was implemented under the guidance of Professor Dapeng Mu. Okay. So here is today's agenda. Okay. So firstly, I would like to give a basic overview of the idea. Then I would like to give an introduction and then explaining the idea, and then I would like to tell what motivated me to do this project. Then I would like to explain the few concepts and algorithms which I have used to implement the idea, and then finally the conclusion and the references. Okay. Abstract. So computerized image analysis of microscopic cells and tissues for detection of various diseases is carried out today. Okay. So the diseases can be detected by observing the anomalous structure, size and shapes of the cells and the tissues. Okay. So sickle cell anemia can be detected, acute lymphoblastic leukemia can be detected, tumors can be detected with the help of computer vision and image analysis. So we propose a algorithm to carry out blood cell segmentation, microscopic images of blood smear, and then find out the shape features of the cells. And after finding out the shape features of the cells, we can detect acute lymphoblastic leukemia. So our idea is to do segmentation, then shape analysis, and then finally clustering to detect acute lymphoblastic leukemia ALL. Okay. So now introduction. So what is ALL first of all? So ALL is a type of cancer which mostly affects children and adults above 50 years of age. And like all other types of cancer, there is an uncontrollable proliferation of white blood cells, WBCs or leukocytes in ALL. So here there is a rapid uncontrollable proliferation of lymphoblasts, which is a type of WBC, a white blood cell. Hence it has got the name acute lymphoblastic leukemia. So to detect ALL is cumbersome because it shows common symptoms as other diseases. So image analysis of the blood smear needs to be done to detect ALL. The conventional detection is very time consuming and requires a skilled hematologist. So an automated process is needed, and this can be done using computer vision algorithms to detect ALL. So we propose a marker based watershed algorithm to basically segment the cells and then get the shape features of the cells. And after getting the shape features of the cell, the clustering is done using k-means clustering to classify the cells. And then after the clustering, we can come to know which cells are healthy or which cells are leukemic, and we also get a count of the healthy and the leukemic cells. And this is how we can detect ALL. Okay. So ALL can be detected using image analysis using our algorithm. Okay. So the motivation, what motivated me to do this project? Okay. So as we know, ALL is life-taking disease, and if it is not detected at an early stage, it can be dangerous to a person's life. It mainly affects children and people above the age of 50 years. And also detection of ALL is a cumbersome task and requires a skilled hematologist. So automating the task of detecting ALL is very important. So thus our system can be a boon to hematologists and make their work easy. Okay. Now I would like to explain the concept of image analysis. Okay. A blood smear microscopic image primarily consists of red blood cells and white blood cells. Okay. So RBCs and WBCs. This can be shown from this picture. Okay. So the red blood cells and the white blood cells are shown. The red blood cells are the red ones and the white blood cells are shown in blue. Okay. So we need to separate the WBCs from the RBCs and the background using image segmentation. Okay. So I would like to first explain ALL first. So as we can see, here's the difference between a normal blood smear image and a leukemic blood smear image. Okay, so as we can see on the right, there is an uncontrollable proliferation of white blood cells in ALL. So the number of WBCs drastically increases as compared to a normal blood smear image as shown on the left. So this is the basic difference. So we need to first separate the WBCs from the red blood cells, and then we need to find a count of the white blood cells in the given sample and find out the shape features of the cells to detect if they are healthy or leukemic. Okay. So and after finding the shape features, we can detect if the cells are healthy, and then we can do a comparison between the healthy and the lymphoblastic cells, and so that's how we can detect ALL in a given blood smear image. Okay. So the methodology to do the segmentation, first of all, it involves a number of steps. So the processing involves a number of steps for segmenting the image and getting the shape features. So firstly, thresholding is done by Otsu's binarization to get an approximate estimate of the cells. Then the noise is removed using morphological opening and closing. Okay, a marker-based watershed algorithm is used to segment the cells. Then contours are drawn on the segmented image and features of the cell are extracted. So after contours are drawn, the features of the cells are extracted. Okay. Then the clustering of the cells is carried out using the data set of the features using k-means clustering, and then the results are plotted. So after the clustering, we get a count of the RBCs, the healthy WBCs, and the leukemic WBCs after the completion of the algorithm. So this is the system overview. So this is just what I said. Okay. So now I would like to explain each of the individual algorithms which I have used. Okay. So first, thresholding and noise removal. So firstly, the image needs to be enhanced using contrast enhancement using histogram equalization. So after enhancing the image, the thresholding is carried out using Otsu's binarization to get an approximate estimate of the cells. Okay. Then the noise is removed using morphological opening and closing. So morphological opening removes the white noises in the image, and morphological closing removes the small holes in the thresholded image. And after implementing thresholding and noise removal, we get a basic estimate of the cells. So as we can see on the left, we have our input image, and after thresholding and noise removal, we get a basic estimate of the cells. Okay. Now we need to carry out the segmentation using the watershed algorithm. Okay. So I would like to explain the theory and the concept behind the watershed algorithm. So after any image has been converted into grayscale, the grayscale image can be viewed as a topographic surface with high intensity where high intensity denotes the peaks and the hills, while the low intensity denotes the valleys. Okay. So, and after that, different colored water labeled is filled in the isolated valleys, local minima. Okay. So as the water rises, depending on the peaks, gradients nearby water from the different valleys, the colors will start to merge, because we are filling the valleys with different colored water, and after a point of time, the different colored water will start to merge. So to avoid this, we create barriers. Okay. Then we continue filling the water and building the barriers until we get a segmentation result. So this is the basic philosophy behind the watershed algorithm. Okay. But to implement this, the noise or the irregularities in the image has to be removed to avoid over segmentation. So we implement a marker based implementation. in of watershed algorithm. Okay, so we need to specify, first of all we need to specify the value points, and then the region labeling is carried out for the objects we know. Okay, so we give different labels to the objects we know. So one label is given for the sure background of the foreground of the object. One label is given to the background of the image of the object, sorry, and everything else is label 0. So we are giving labels to the foreground, the background, and the region which is unknown. Okay, so if we are sure if a particular region is a part of the foreground of the image, we give it a label 1. If we are sure that the particular region is a part of the background of the object, we give it 0. Sorry, we give it another label, and then everything else we label 0. So these are the markers. Okay, then we apply the watershed algorithm. That is, we continue filling and building, filling the peaks, filling the valleys with different colored water, and then building the areas until all the peaks are in water. Okay, and then the markers will be updated and the segmentation will be done. So this is the basic concept behind the watershed algorithm. Okay, so the reason why we are using the watershed algorithm is that basically the cells are overlapping, or their cells are touching. As we can see here, few of the cells are touching and they are overlapping. So it becomes difficult to segment them using conventional or traditional segmentation methods. So we are using the marker based watershed algorithm basically because of that reason. Okay, so after the segmentation is done, we draw contours around the cells, and then after that we extract the various features of the cell. Okay, so the various features which we are extracting are the area, perimeter, form factor, solidity, convex area. We extract these features for each and every cell in the image, and then the data set of each cell is put into vectors. Okay, and then the vectors are classified using k-means clustering. Okay, so this is the output of the contour detection. As you can see, the contours are drawn around the outline of the cells. So as we can see, the segmentation results. Segmentation detects most of the cells in the image, and after that we find the features of the cells, each and every cell. Okay, yeah, and the features are very important to classify the cells using k-means clustering. Okay, now after finding the features, we select two of the most important features, which are the form factor and the solidity, and we use it to classify the cells using k-means clustering. So I would like to explain the basic algorithm of k-means clustering basically. So the clustering starts, it's an iterative clustering method. So the clustering starts by selecting any two centroids, K1 and K2, which can be points from the dataset, or it can be random as well. Then the Euclidean distance of each point from the centroid is calculated. If the dataset is closer to K1, we label it some number, say 0, and if it is closer to K2, we label it 1. Over here, we are creating only two classes of cells. That is, we are creating two classes of cells, that is the healthy cells and the leukemic cells. Okay, so hence the value of K is 2. We are taking only two centroids. Okay, so the value of K can be anything. It depends on how many classes that we want to create. So here we are creating only two classes, hence the value of K is 2. And now after selecting the centroids, we find the Euclidean distance of each point from the centroids, and then after getting the distances, we see whether the data set point is closer to K1 or K2. So if it is closer to K1, we label it as 0, and if it is closer to K2, we label it as 1. Then we find the average of all points with one label separately. So the average of all points with the label 0 is found separately, and the average of all points with the label 1 is found out separately. Okay, and this will be the new centroid. Okay, so then the procedure, the above steps is carried on again and again till a precision level is reached or a maximum number of iterations have been reached. So the centroids are being calculated again and again until a precision level is reached. So after a number of iterations, or after a certain level of precision has been reached, we stop the process, and that is how we do the clustering. Okay, so we have implemented the algorithm by taking the form factor and the solidity of the cells, and then we have classified the cells as if they are healthy cells or they are leukemic cells. Okay, so these are the results of the k-means clustering which we have carried out. Here we can see that the red cells represent the leukemic cells and the blue cells represent the healthy cells. Okay, so the cells have been classified according to their form factor and their solidity value. Okay, yeah. So finally the conclusion. Okay, so RBCs and WBCs can be accurately detected using the watershed algorithm. Then the overlapping cells and the touching cells are also accurately detected using our algorithm. And after clustering, we can get a count of the healthy and the leukemic cells, which is very important for detecting ALL. Okay, so if the count of cells is of the leukemic cells is very high, or the abnormal cells is very high, we can detect if the sample has ALL or not. Okay, and after clustering we can get a count of the healthy and the leukemic cells, and so it becomes easier to detect ALL. Okay, and thus the segmentation and counting of the cells is automated, and the valuable time of the hematologist is saved using this system. So these are the references. Okay, yeah. Thank you. Now I would like to give a demo of my project. Okay, so I've implemented my project in Python. So I've used various libraries like OpenCV, NumPy, etc. to implement the idea. Okay, so this is my code. Now I would like to run it. Running. Yeah, so this is the input image which I am taking. So as we can see, there is a presence of lymphoblast in the cell, lymphoblast in the image. So this is the segmented output which I am getting after implementing the watershed algorithm, and the contours are drawn around the images, around the cells, as we can see. Okay, so this is the Python shell where we get the values of the different parameters, that is the form factor, area, that is the various features which we have extracted. So these are the various features, and then they are put into vectors. Okay, so after the segmentation and after the clustering, we get the count of the RBCs, the WBCs, the number of healthy WBCs, and the number of unhealthy or the leukemic WBCs. So this is done after clustering. Okay, so after getting the features, we calculated the solidity and the form factor, and then the cells are classified using the solidity and the form factor of the cells. Okay, and so this is the same plot. Okay, of the solidity and the form factor, and so this is how this gives the cells. Okay, Thank you.